All right, welcome back for the that's shiny for the final afternoon of the workshop and the last full talk but of the program. But we have a bunch of lightning talks at 3:30, so stay tuned for that. But we have Lin Lin today talking to us about rapid quantum ground state preparation via dissipative dynamics. So take it away, Lin.
Yeah. First, I'd like to thank the organizers for inviting me. I'm sorry I haven't been participating in the workshop. It's a very exciting workshop as much as I could. Well, there were a few expected absences, but there were a few unexpected ones, including food poisoning yesterday, so I might sound a little bit weak. So sorry about that. Also, I was planning to modify this talk quite a bit before the talk, but because of this, I couldn't. So if some of you have seen a version of this talk before, I apologize. So this is a joint work with a number of people. Oops, I don't know what this is happening. So some earlier works joined with Anthony and Jian, who now just joined Michigan as an assistant professor in the math department. Some work joined with Hao and Li, who is a Tsinghua undergrad student in chemistry, but will join Berkeley math as a PhD in a month, and also Yun Tao from Caltech. And then there's this work joined with the Caltech team, in particular with the Garnet Chen and the John Presco's team. So, well, the importance of ground state preparation and ground state energy estimation, I don't think I need to emphasize that. They're just the two examples from strongly correlated chemistry and also the strongly correlated condensed matter physics like Hubbard model. Even for the Hubbard model, we're interested in the thermal phase diagram. It is still very, very interesting to figure out the parent state, which is at the zero temperature. So they indeed are relevant. I think yesterday there has been a lot of discussions, including panel discussion on that. And so to set up the problem, we are given a Hermitian matrix H, and we would like to estimate the smallest eigenvalue to precision epsilon, and if possible, prepare the ground state. Very well known that it's theoretically intractable in the worst case. One standard assumption to go around it, not the only assumption, is to assume there's a good initial state in the sense that the many-body overlap is big. It's sufficient to be omega 1 over poly n, but let's say bounded from below by a constant like 0.01, 0.001 would be good. In the past few years, we have also been mostly interested in methods with performance guarantee under some assumptions. This means that it could be combined with some heuristic methods such as VQE to prepare this good initial state. So the dominant method is called a quantum phase estimation, and numerous versions of a post-QPE methods. They all work in the same way. You decompose the initial state with respect to the energy eigenbasis, and then you see, hopefully, there is some overlap with the ground state, but also overlap with some other states. Then you run, one way or another, a filtering algorithm, so the unwanted eigenvalue contribution is suppressed, and you keep the wanted part. This strategy works if we allow repetition by 1 over P0 times. You can achieve optimal scaling 1 over square root of P0, but not further for generic problems. In particular, if P0 is 0, then you have nothing left, and it provably fails. So in the past few years, there has been tremendous progress in understanding the single ancilla quantum phase estimation methods. We can call them post-Kitaev type of methods, but also there are some quantum Krylov and variants of these things. We contributed a number of those. It's a much simpler circuit compared to the multi-qubit QPE. The idea is you provide some evolution time, and you do some very simple measurements. Outcome are just something like plus minus 1 plus minus I, and you do classical post-processing and try to infer the eigenvalue, but doesn't prepare the eigenstate. All those methods suffer from the same post-selection type of difficulty. They all scale with respect to 1 over P0. So Whether this combination of strategies, that is, we prepare a good initial state and then do one way or another QPE type of methods, is sufficient, is an evolving story. In particular, that good classical state must come from a classical description. And a natural question is, given a classical computer can prepare a good initial state, is the problem still hard? I believe that yesterday, Jiaqing's talk and during the panel discussion has discussed some aspects of this. We don't have a full answer to this. Theoretically, what we're comparing is whether quantum computer, which achieves 1 over epsilon, precision epsilon with order epsilon inverse gates, is good enough to beat classical refinement strategies, which could be cost can be exponential in 1 over epsilon. And last year, Garner Chen, in this invited lecture on Faraday discussions, discussed this in detail. I recommend you to this paper if you haven't read it before. Well, Fimoco was considered to be a poster child problem for quantum simulation. For a long time, we just don't know whether we can construct a good enough state to overlap with, it's called psi zero, but we all think it's most likely some low energy states. We still don't know for sure. So a lot of extrapolation arguments are used here, but it is actually possible to construct an initial state with believed to be reasonably large overlap. I want to emphasize that even when you have a 0.99 overlap, the energy, absolute energy, can still be quite far away from chemical accuracy, because you just have a little bit of energy components in the high energy, immediately the energy is very much off. So it doesn't disprove this statement, but this probably won't be purely answered theoretically, and we need more evidence in the next years. This talk is about a completely different question, whether we can prepare the ground state efficiently, starting from any state, in particular with a zero overlap. But it can be exponentially small. It doesn't need to be strictly zero. Any questions so far before I switch? Okay, so for this audience, well, you have been either just exposed or have seen this a couple of times before. The answer is dissipative dynamics. And the idea is that you have a system coupled with the environment. And this is an old idea and has been studied in physics and chemistry for many decades. And even the algorithmic idea is not new, because it dates back to the Lin and also at the same time, the JKS paper together, we call it JKSL formalism, or Lin formalism for short. And also Davis did like foundational works also in the 1970s. People know that there exist some effective dissipative descriptions that are Markov-like, and to describe this system environment interaction, at least approximately. But the formalism goes much more beyond that second order expansion type of argument. In fact, these stand on their own and can be viewed as algorithmic tools. If we just talk about like that, it's a little bit empty. What has happened in the past 3-4 years is really there have been very concrete progress in developing these algorithmic tools. And we're still in the process of understanding how powerful they are. One question is whether we can simulate them. There are two types of dissipative ones. The Lin dynamics I just mentioned. So it's d rho dt equals to 3 components. There's a coherent term that's like a Hamiltonian simulation. There's a pure dissipation, and then there's a transition. So act together, this generates dynamics that can be described by a quantum channel, means CPTP. If we're interested in short time simulation, or in some fields for different reasons, we drop this transition term, and then this is a wave function-like description called the non-Hermitian quantum dynamics. In the past few years, really high-order methods have been developed for all these things. So throughout this talk, whenever I write down a Lin-Blad dynamics, I'm just going to assume it can be efficiently simulated on a fault-tolerant quantum computer unless mentioned otherwise. So we won't talk about the simulation technique at all. We'll just worry about the dynamics itself. So the idea is related to thermalization or cooling. Well, cooling is something we experience every day. This is a very classical fridge. This is still a pretty classical fridge, although it looks very quantum. This is the fridge we're talking about. It's really looks like a system ancilla or bath interaction. There are many variants and incarnations of this description. It doesn't look like a Lin-Blad equation at all, but I want to say that the connection are being very actively explored just in the past few months, actually the past month, just 1, 2, 3, or maybe 4 papers on this thing. And I think where the community is getting a much better understanding at the algorithmic level, understanding the connection between this system bath interaction and the more complicated, seemingly more complicated Lin-Blad pictures. In short, Lin-Blad provides at least a theoretical tool for us to understand the power of this system bath coupling picture, which is non-Markovian and much harder to understand, but we're not quite sure at this moment. So one natural idea to prepare the ground state is to prepare a thermal state. Indeed, this seems to be how nature does it. So we can do a Gibbs state preparation and then drive temperature to 0. So one thing that has happened in the past 2 years is really for the first time this exact detailed balanced Lin-Bladian that can be efficiently simulated and coupled with some proof techniques even proved to be efficient. So the breakthrough came from the Chen, Castellano, and Gideon paper. And there are a couple. Now we think we have a pretty good understanding of how this KMS detailed balanced Gibbs sampler behave. They indeed generalize the classical detailed balance condition naturally for a set of non-commutative Hamiltonians. Let's now take temperature to 0 and try to prepare the ground state. It's a completely legitimate process, but implementing the quantum detailed balance has this overhead. In the very worst case, we need to go to temperature that scales with respect to the system size, which is counterintuitive because we always, even for a microscopic system, we say temperature at 1K. We never say temperature equal to the system size. Of course, that's like a worst case scenario. A very thorny issue for theorists is that the proof of the effectiveness of the mixing time usually involves factor exponential in beta. That's actually the best case. Usually, like most of the time, it just doesn't work at all beyond the constant threshold. So that means if beta is On, that means in the best case, it scales exponentially in N. You are not gaining anything. And in the Euro case, you just couldn't say anything about the ground state at all. If you haven't seen this formalism before, a take-home message for you is that the ground state preparation can be much simpler than thermal state preparation. Well, if you came from the thermal state side, this may seem counterintuitive, but really it is not. Let's just think in the classical setting, the counterpart to ground state preparation is nothing but optimization. In optimization, we can run gradient descent with larger or smaller step sizes, and they're fine. I mean, they converge to local or global minima, that's fine. But if you want to prepare a thermal state, you need to be much more careful and try to preserve this or that. So that's the analogy. So if you're interested in ground state preparation, you should expect it to be in some sense easier. Of course, in the worst case, it's still very bad, but in some sense, it's not necessarily harder than thermal state preparation. Show you a toy example how this thing works. 2 by 2, my Hamiltonian H equals to minus Z. So if the ground state is just 0, 0, I start from the first excited state, has 0 overlap with the ground state. I choose this K to be an annihilation operator, which is cheating, of course. The solution converges exponentially to the ground state. In fact, not only starting from this state, it converges exponentially. It actually converges to the ground state exponentially fast from any initial state. The process is trace preserving, as you can see. This means there's no post-selection. It will just work with the probability 1. And this is not a detailed balanced process, and it's pretty efficient. So it didn't prepare any thermal state, and yet it can prepare the ground state. But this is cheating because I chose this specific K. When I have a more complicated H, can I find one or many such Ks to prepare the ground state? Well, let's look at some of the ingredients behind this very simple example. The LK, the thing that does most of the work, it pushes high energy states to low energy states because K is an annihilation operator. Second is that it fixes the ground state. So if you plug in the ground state, the dynamics is fixed. So if we want to generalize this principle to more complicated systems, there's a name called the dissipative state preparation or dissipative state engineering, has been studied by many people before. One common question is whether there's any connection to adiabatic state preparation. But to my knowledge, other than both are BQP complete strategies, I don't see a direct connection. There are also experimental talks, like a way of thinking about this process, and they're more robust, maybe. But whether this strategy is good enough to prepare the ground state efficiently for non-commuting Hamiltonians, a lot of people I talked with, they actually, for a while, they thought that this is not possible for good reasons, because of certain experimental constraints. But what I'm trying to say is this actually is very simple. So you just follow a very explicit recipe. Whether it works or not, we don't know. But here's a recipe, and the rest of the talk, we talk about in which case it could work. So the idea is we want to write down Lin-Blatt dynamics. It's always CP-TP, in particular it's TP. So if you look at the dynamics in the energy eigenbasis, the sum of all the contributions is always equal to 1. If I can engineer the jump operator so that the mass moves from high energy states to low energy states, but not the other way around, sometimes it may make one step, sometimes it may jump multiple steps, and then we might have be able to prepare the ground state and start it from anywhere. So the ingredients here, one thing is this A called the coupling operator, which I'm going to talk about it. Then there's a filter called F. I'm also going to talk about it later. And the rest, there's just no other degrees of freedom to design. And if you're familiar with the recent developments of thermal state preparation, this is even simpler. Well, shares a lot of similarities, but also is even simpler than that. So how to design this jump operator? There are two components. Let me talk about the F part first. You do the resolution of identity, so here and here. And you find that these are the eigenstates. You will end up with a Fourier transform of the Fs, denoted by F hat. If I want to only have high energy to low energy transition, all I need to do is to make sure that F hat omega is 0 in the positive energy axis and non-zero in the negative energy axis. You immediately find that this fixes the ground state. There's nowhere else to go. It pushes from high to low and not low to high. Of course, the strategy works only if there are sufficiently many of these entries that are non-zero. There should be a path, at least there exists a path from any state to the ground state, jump many steps in between. And that's the job of the coupling operator. Another information is that the coupling operator can be simple. It can be local Pauli or Mariana or something like that. This is a concrete example of a TFIM with A just to be chosen to be Pauli X1. If we view A in the computational basis, this is just a 0, I0, so it's very sparse. But what we care about is whether A is sparse in the energy eigenbasis. That means if H is classical, it's diagonal, this doesn't work. Actually, interestingly, non-commutativity helps. So in the energy eigenbasis, you couldn't see this very clearly, but you will see like there are a lot of non-zero entries. That's one. Two is that from high, this is the ground state. I don't have a direct connection, go from high energy states to the ground state. But I can jump from here to here to here to here to here, and then hopefully it jumps to the ground state. And another feature is that this is upper triangular matrix. And this is important because that's by design of the filter function f. So one possible concrete choice of f works in practice. Theoretically, you still need to do a little bit of a cutoff to make it clean, is this. All you need to know is the lower bound of the gap so that make sure that there is some energy transition from 0 to roughly by a size of a gap. You should reach some omega 1 value. And it should decay off after at least like a constant sized energy. But at most, this is a spectral radius. So you only need to know some very coarse-grained information of the system. And yes? Can
you say why the gap is the important one?
Oh, the gap, because otherwise, let's say this stays to 0 for too long. I'm at the first excited state. It couldn't go to the ground state, right? Yeah. So this couldn't.
Jump up immediately, yeah. Because
right. If you jump up immediately, then f decays too slowly in the time space. Yeah. So there's a sweet spot. It couldn't. This strategy couldn't violate the energy time uncertainty principle. So because K needs to, the efficient construction needs to truncate this and discretize and then use a linear combination of unitaries. So the decay of f matters. So with the proper choice of f is smooth and also decays fast, which means it can be truncated and discretized efficiently. Then theoretically, you can just plug in this K into the earlier high order Lindblad simulation and get this whole thing running.
Lin?
Yes?
Can you think of this as having a relationship to regular gradient descent?
Yeah, so the question is, I guess I don't need to repeat the questions. Yeah, you have that, yeah. So it's actually a very interesting question. It's more like indeed, when you have one thing, it looks really like a gradient descent, but it's just not like the steepest direction, right? It's some averaged. When you have multiple jump operators, you're descending within the ensemble of directions. Yeah, right. Yeah. So that's indeed the right analogy. Yeah, Ehud.
So at least naively here, it looks like A will have to grow to pretty large size if it wants
not
to.
Not necessarily. Yeah.
Well, not in.
Oh, you mean K?
Not
K.
Yeah, K. Sorry.
K,
yeah, A
right,
will grow to a large size, and K will be.
No, K. A doesn't. We'll show later. But K maybe.
Yeah, I mean, A is the growth. K is more or less the growth of A filtered.
Yeah. But A can be local.
Yeah, A is fine.
Right.
The problem is that
grow.
Yeah, but you want to construct an operator K that you can actually.
Right. Okay. That's my next slide. Yeah. So the question is how to actually simulate this thing. I mean, an experimental setup. That's the connection with this recent interest a number of papers. But really, so this diagram already happens here. It provides a single ancilla-based simulation algorithm for one, but also multiple jump operators. They're actually pretty simple. The point is that this integral can be, you don't need to construct it even. You just be able to do some Hamiltonian simulation, do a rotation with respect to A. If A is a single Pauli operator, this is just a 2-qubit gate. Do a little bit, do a little bit, do a little bit, and then you mirror and discard, you're good. So there exists this kind of a single ancilla-based implementation. But conceptually, you're absolutely right. K has to be quasi-local or becomes larger. And that was the reason why some group of people previously thought this couldn't be used to prepare the ground state of non-commutative Hamiltonian. Because if you restrict to completely local jump operators, there are theorems showing you couldn't do it.
So is it quasi-local or?
Quasi-local. Interestingly, at least to some experimental physicists, quasi-local means local in the computer science setting. Because their definition of local is like literally one local or like two local at most. And the quasi-local is already a group of things. But here is the computer science definition of quasi-local. Any other question? Yeah.
Is there a notion of like Hamiltonians that are convex or where the gradient descent works and then?
Great question. I have no idea how to answer that. Yes.
Do you always get stuck in local minima?
We'll see how that works later. Yeah. This is just the algorithm part. I don't even know how to define local minima. Okay. So now I've already talked about the algorithm. The question is whether it is rapid. So I'm going to talk about two things. One is the numerical evidence and also some theoretical evidence. Our motivation was quantum chemistry Hamiltonian. There isn't a lot of structure going on. So we came up with two sets of jump operators. Type 1 is all the creation annihilation, which is a lot. Well, wait for type 2, which is the product of the creation annihilation, which is even more, but still polynomial in the system size. So this one is, you need to be simulated in the Fock space, and this one you need to simulate it, you can simulate it with the Fuzzi in the particle number preserving space, which is a lot cheaper actually. So what we found is for linearized Hartree-Fock, if you look at in the molecular orbital setting, this will independently adjust the population and all the way to satisfy the so-called Aufbau configuration, which means that there are a set of occupied orbitals, there are a set of unoccupied orbitals. All the occupied ones are fully occupied, unoccupied are fully unoccupied. So that's the generic behavior for non-interacting systems. And the rate is universal, is independent of anything. It's just e to the minus t. For the quadratic ones, that's like mass preserving, even within the 1 RDM. So it will move things around, eventually move to the Aufbau principle. This can be proved. So this shows how that works. For a range of molecules, a range of bases, a range of orbitals, number of electrons, they're all exactly the same rate. There is no dependence whatsoever. For the type 2, and it only depends on coarse grained information, such as the number of orbitals and number of electrons, and doesn't depend on anything else, like the basis or geometric configuration. Of course, we're interested in how this works beyond linearized Hartree-Fock, which is just quadratic. So this is a full ab initio calculation for a range of molecules. And the idea is that they all converge to chemical accuracy, and the mixing time, they don't differ too significantly from the Hartree-Fock. A factor of 2 is really, theoretically, is nothing. This can solve strongly correlated systems, prototypical example is H4. You just increase the bond dimension, and the couple cluster methods are, this system is designed to make a couple clusters fail. As the bond length increases, the accuracy of the couple cluster methods gets worse, and Lin blood dynamics can all converge to the below chemical accuracy. What about condensed matter systems? So this is an example which is a TFIM, which is fermionizable, so still very simple. We further choose the coupling to be operators on the boundary, so just X and Y on two boundaries. So physically it's a little bit counterintuitive because there is a lot of heat in the middle of the system, and you're only cooling on the boundary. So some mechanism must happen to bring the heat from the center to the boundary to let it cool down, and that is where the Hamiltonian term is useful. But the idea is what you can show numerically in various ways, such as measuring the energy and also measure the inverse Liouville gap. The system, they all mix, and the time scales cubically with respect to the system time, system size, and this can be theoretically explained. That's what I'll show later. Generic formalism to explain this behavior. A slightly more, slightly fancier thing is this cluster state Hamiltonian. It has a slightly non-trivial phase called the SPT phase with a non-vanishing string order parameter. There are two phases. One is a paramagnetic, and the other is this SPT phase. So this shows that starting from the paramagnetic phase, it will be driven to the correct SOP phase. And the convergence rate scales cubically with respect to the system size. Here, convergence is a little bit tricky because the ground state manifold in the thermodynamic limit is actually fourfold degenerate. So what do we mean by convergence? So the degeneracy actually is due to the edge states. This has nothing to do with the bulk properties like SOP. So the gap here we're talking about is really the effective gap, which is between these four asymptotically degenerate edge states and the rest of the states. And that converges cubically with respect to the system size. For non-fermionizable systems, we need a bit more tool. We developed the tensor network-based simulation algorithm. I won't have time to talk about this in detail. If you're interested, I'm happy to explain this. Yeah.
So for the degenerate ground space, do you converge to a particular ground state depending on your starting configuration?
I couldn't state a priori where it is converging to, but the point is it doesn't matter because they share the same SOP. Their SOP is a bulk property.
Okay.
It doesn't touch, it can be defined without worrying about the boundary. Okay, so we developed the tensor network-based methods. Compared to standard tensor network methods, the new thing here is the jump operators are pretty big. So we're really propagating MPOs like at every moment, every step. So that's the expensive part. Other than that, things are relatively standard. So you need to construct an MPO representation for each jump, which means MPO representation for this big integral. There are multiple ways to do it. I think there's definitely a lot of room for improvements, and we have a lot of experts even in the room to do this type of thing. We just did the easiest. And then we just use a relatively simple integrator to integrate it. This allows us to study things that Hamiltonians couldn't be fermionized, but also even for fermionizable Hamiltonians, if you choose A to be not on the boundary, you couldn't convert that to a so-called quasi-free dynamics. So they all need this tensor network-based simulation methods. So the cooling is called the bulk cooling. That is, you apply X, Y, Z to each side. For those working on thermal state, this should be very familiar. And observed mixing time is log n. And at least in some regime, we could explain this.
Question?
Yes?
What did you mean by by fermientization?
Oh, a good question. So fermientization is for 1D chains. I can just use the Jordan-Wigner transformation and write it as in terms of fermionic operators. Due to the 1D structure, the signs they cancel, and so for some models.
You would call the inverse direction of Bostonization then?
Inverse direction, I don't know. The inverse direction, I don't know what it's called. Yeah.
So all the plots you showed don't depend on the initial state now? Or?
They don't depend on the initial state at all.
So you have to just
No,
pick any n.
yeah, that's the idea. Yeah, yeah, yeah. So, the theory part was what I hoped to add a little bit last night. That was the original plan, but I feel pretty miserable, so I didn't have time to add the slides. But if you have a question, feel free to ask me. So at least I'll be able to talk about what the results are. So the standard for characterizing the mixing time is through the trace distance, which is starting from anywhere. That's the important thing. You evolve this Lin-Blah dynamics for time t, mind the distance, trace distance, with respect to the invariant stationary state is bounded by epsilon and eta. And this eta, you can just set it to be 1/2, and that's hard enough. So the existing analysis, they are mostly for the thermal state. In particular, there are two main ways to do it. When we have this KMS detailed balanced Lin-Blahdians, we can prove the spectral gap of it. There is actually a factor you need to pay between the spectral gap and the mixing time. So it will always prove something that's a poly n and the system size mixing. Some people call it fast mixing. There is a much more technical route called the log Sobolev or modified log Sobolev inequality to prove some entropy production. It's harder to prove, but gives you stronger results when you can do it. And T mix will be poly log n, and some people call it rapid mixing. So if this is the first time you hear what's fast, what's rapid difference seems hair splitting, you're not alone. But after a while, you get used to it. So in all these kind of things, the sigma needs to be invertible. But the ground state is by definition not invertible, and existing tools, most existing tools, they are not applicable. Any question so far? Okay, so what we can say for the first thing is quadratic Mariana system. Just a very quick introduction to quadratic Mariana systems. So these are Hermitian operators satisfying this anti-commutation relation. A quadratic Mariana Hamiltonian means that H is can be written as a coefficient matrix HBQ times WPWQ, where H is purely imaginary. This may look a little bit exotic, but it really includes all the standard quadratic fermionic systems. Includes the 1D TFIM with open boundary gradation, includes the cluster state Hamiltonian you have seen, and cover all the quasi-free Lin-Blah dynamics in the sense of a person. But if you're interested in this direction called either quasi-free dynamics or some technique called the third quantization, the paper I strongly recommend is this nice paper by Bathiel and John in 2022. What we can prove is that for any quadratic Mariana Hamiltonian H that is gapped with a unique ground state sigma, if you choose any way to choose linear or their linear combination of linear Mariana coupling operators as a coupling and use them to generate the jump, you choose some W to be the coupling and then generate a jump through that integral thing. Then rho t converges exponentially to sigma in trace distance. And the convergence rate is very explicit. There is a gap, there is a condition number, and then there is a system size dependence in the log. Here, the delta and v, they are eigenvectors and the gap of a non-Hermitian coefficient matrix. And we know what that matrix is. So there are two immediate corollaries. With a very simple calculation, we can find that for bulk dissipation with Mariana coupling operator, all the Mariana coupling operators, that is the case when we do the type 1 for the linearized Hartree-Fock. You can immediately compute kappa v equal to 1, delta equal to 1/2, doesn't depend on anything. And this proves the universal convergence. This is the trace distance, and the energy, you square that and get e to the minus t, as you have seen before. For TFIM with boundary dissipation, with a little bit of a perturbative argument, and you will be able to show this n to the minus 3. And it explains the n cubed log n scaling seen numerically. Numerically, we couldn't distinguish the log n, but the n cube is very clear. What about non-quadratic systems? Because we're definitely not building this machinery to solve quadratic problems. The best thing we can say so far is weakly interacting systems. What it means is I start from a non-interacting part and add a little bit of perturbation called interaction. This Hj is geometrically local, and norm is bounded by 1. The perturbation, epsilon, needs to be smaller than the threshold epsilon star, which is a constant. But I want to say that if you measure the size of the perturbation in terms of the operator norm, it is not small because, well, this thing grows with respect to the system size. The theorem is that in this setting, you choose coupling operators to be Pauli X, then mixing time is log n. And there is an analogous result for a certain weakly interacting fermionic systems and log n mixing. I'm happy to talk about the techniques if you're interested after the talk. Oh, yeah.
How does the threshold depend on the non-interacting system? Is it just independent?
For example, the threshold is independent because you have already fixed the non-interacting part. Yeah, here you have some gap dependence, for example. Yeah.
Like, say that it has, for example, some, it's in higher dimensions and you have some...
Yeah, the higher dimension doesn't quite matter. It's just some gap assumption.
Even if there's an obstruction to localization?
Beg your pardon?
Even if there's an obstruction to localization?
Oh, the question is whether there's an obstruction of localization. I think maybe, yeah, so we have a M that's specifically designed so that you have already done all the doubling, all the rotation, etc. So the ground state is a trivial state. Yeah. So that has been handled by all the doubling tricks and etc. etc. Yes.
So for the bosonic system is very easy.
No, there's no bosonic.
The spin system. I mean.
The spin system. Yeah.
Yeah. I mean, so the non-interacting part is gapped, right? So how does this T-mix compare with what you'd get for the time for adiabatic state prep?
Well, probably no advantage. Yeah, I don't know. Yeah. I'm not saying. Yeah. So the short answer is I don't have evidence showing this technique must be better than adiabatic state.
Yeah, I guess the question is more like, so if is the upper bound on epsilon you have there in order to bound the gap?
Yes. Yeah.
Right.
So it's a gap statement, but it's the Lin-Bloddy gap. So it's I don't have a direct way to compare.
Right. Thanks.
So as I said before, even if it boils down to a gap, it's still non-trivial. The reason is that there is a conversion factor from gap to mixing time, and that factor blows up as beta goes to infinity. So even if you can prove there's a gap, you're still not there to show convergence in trace distance. So there's indeed some technique that's involved there to show to be able to show convergence in trace distance at all to converge to a pure state is something haven't been done before. Love you.
To add to that, like, just knowing that the Hamiltonian has a gap doesn't necessarily tell us that there is an adiabatic path that remains gapped throughout, right?
Right. So, again, I'm not claiming any advantage so far.
I know. So,
all right. Oh, right.
You can't even claim that the adiabatic algorithm has something comparable.
Oh, that's right. Yeah, you
Because
still
it
need to
doesn't
find a
give us
path and
Exactly.
et cetera, et cetera. But in this case, I guess the question is whether the gap is so large that there could exist such a path. Maybe. I don't know.
Yeah, I was thinking that the upper bound on epsilon would basically be telling you that you can. That
Yeah,
are
there
guaranteed
exists a
that.
path.
Yeah.
Maybe. Yeah. But in any case, it's what we see so far is it's a very different mechanism. Maybe there's some deeper connection, but definitely, as I'm going to conclude, we're not claiming we're solving any hard problem yet.
And what was the dependence of the mixing time on the gap here? For the spin system.
For the spin system, the gap is just constant, so it's a very simple non-interacting.
Is there a dependence on epsilon?
The question is how does epsilon depend on the gap? I'm saying the gap here is a constant. How does epsilon star depend on the gap? So yeah, it's a very fixed system just to show this thing works at all. That's the goal. Yeah, we think this provides some evidence showing that it enhances the understanding of the power of dissipative state preparation for non-commuting Hamiltonians. And we think the tools here could possibly be useful for other things. I mentioned before that recently there's quite a surge of interest in exploring the early fault tolerant or even near-term implications. I personally don't know whether this is near-term enough. Some people are more optimistic than I am, but I do think that this is at least quite early fault tolerant. Whether this solves any hard problem, Anthony came at the right time to answer this question. But whether we can go some beyond perturbative regime, that would be great. I don't have any ideas, and hopefully you have better ideas. And thank you very much for your attention.
Would you encourage us to think about non-commuting Hamiltonian and use refracting codes?
Oh, such a deep question. What's the advantage?
Well, I mean, you could use your dissipative dynamics as a means of.
Yeah.
So if you have understanding of initial state insensitivity of your dynamics, then it could be used as a refracting code. But you are emphasizing that it applies for non-commuting Hamiltonians. Directly apply, but
yeah.
What's your thought on that?
I don't know. What's the advantage? Let's say even if such a thing exists, and what can you do that you couldn't do now?
It's kind of self-correction. You know, you design your dynamics in such a way that.
I think the implementation of the jump still requires you to do something. Yeah, maybe.
Yes.
Yeah.
It's more or less fixed to the local region of that space.
I think that I need to ask you offline. Yeah, more specific.
Maybe I don't understand exactly what are quasi-local Lindbladian operators, but if I allow quasi-local operators, say I take Chirac and Wolf algorithm where they locally project to the local ground state in some finite size region, if I take these finite size regions and make them say log L system size, do I get the same scalings as this?
The Chirac algorithm is a very specific algorithm. In particular, I just don't know how to prove the mixing of that at all. Its construction is different, right? I mean, he showed, we're talking about the VWC 09, right?
Yeah.
I mean, he gave a few examples how to do MPS. I mean, what if the state is a PEPS, and there are some graph states. I mean, there are a bunch of very inspiring examples, but I don't see how it directly turns into algorithm. Oh, well, there is another strategy, which is every time locally, if it doesn't work, I revert to some like maximum mix. That one probably doesn't work so well. But all the others, to me, they are special examples.
But I thought there is just like a very artificially created jump operator that simply projects at every kind of box into the local ground state of that
the question
box.
if it doesn't
you
work.
make the box large enough.
Right. The question is if it doesn't work, what does it fall back to? Right? Every projection can fail. Mm-hmm. If the alternative is go back to maximum mix, that probably doesn't work. Right? It's a CPTP, so to make sure CPU must have a plan for every scenario.
Hi, thank you for your talk. So just to clarify about these regimes where you proved the rapid mixing.
Yeah.
Is it the same regime where you could like use the same perturbative arguments to like find, let's say, observables classically, or
We don't
it's not
know.
obvious?
We don't know. I think it's still open.
So okay.
Yeah. We asked some of the best experts in the audience. Yeah. I don't know.
Okay, thank you so much for a great talk. I'm just curious about what the intuition is on why like the initial state can be arbitrary, like compared to like most classical methods for chemistry. I feel like the initial state is very important in actually being able to converge the ground state. So I'm curious as to why it can be arbitrary.
Yeah, the answer is that this dynamics is trace preserving. So post-selection, what it does is not trace preserving, right? So you have something that you say, you see 0, great. If you see 1, too bad, throw it away. That's not trace preserving. This one, the idea is no matter what, the dynamics just goes forward. Even if before, in the context of a post-selection, you get garbage. So that goes back to the VWC. So it's like the idea is what's the backup plan? Right, so Lin provides a backup plan because it's the whole thing is always completely positive and trace preserving. In the energy eigenbasis, this means that it is always just shifting the energies around. It's just if you don't design it well, they just shift around randomly. I mean, it doesn't end up anywhere. But the idea is if you design it carefully, you could engineer this dissipative dynamics and try to make sure that the only thing survives is the ground state.
Thanks. Do you think it might be easier to design algorithms such that the time it takes to reach a polynomial, an inverse polynomial overlap with the ground state is, say, much lower than the time it takes to go all the way to the ground state?
Could you repeat the question? Sorry.
So the mixing time basically captures how long it takes you to shovel all the way to wait 1 on the ground state.
Yeah.
Right? But maybe a lesser threshold for that is just achieving inverse poly overlap with the ground state.
Yeah,
Like,
I
do you
mean,
think-
So I really more view this as one of the ways to get to omega 1 overlap or omega 1 over polyon overlap, right? So we look at what are the options. We can prepare classically MPS and quantum encoded. We can do variational. We can do adiabatic, right? I mean, this is yet another way. Whether this will beat others, I don't know. But if it works, great. And then you just get somewhere, right? Start from there, run a QPE. And that would be the hope. Although this one could possibly go all the way, I don't think going all the way is the most efficient way of using it. Probably just get somewhere,
Right.
You're good enough, and then run QPE. You should be good.
Just a small question about something you said at the beginning. You said that non-Hermitian is also efficiently simulable currently?
Oh yeah. So well,
There must be some
efficient
kind
in some sense.
Yeah.
So the question is how to simulate this thing. Yeah, it's actually a pretty interesting question. This is in joint work with Andrew here and also Dong'an. So yeah, there exists some at least algorithmically interesting ways to simulate it, and very, very efficiently, or to the best extent efficiently. Although this without encountering without going around the post-BQP issue.
Oh, I see.
So to the extent you can do, which means in the end you might suffer from a success probability issue, but there's just algorithmic lower bound. There's nothing you can do about it. And other than that, you design algorithm that's as efficient as possible. If that's your question.
I guess the point being that you can simulate diagonalizable non-Hermitian operators then.
Yeah. I mean, so if there are some complexity difficulties. Of course, no algorithm, including these ones, can overcome.
Right. That's fine for me then.